Hi, everyone, and welcome to our webcast today, Zone-Based Design with CATIA Composites Workbench, featuring Iouri Apanovitch. Iouri, the floor is yours.
Oh, good day, everyone. Welcome to the webcast. So the topic for today's webcast is Zone-Based Design with CATIA Composites Workbench. As we all know, composite materials are now pretty much a hot topic in aerospace industry as well as in many other industries. And great things are happening in here, which means we see some new players on the market. And CATIA and Dassault introduced their Workbench quite a few years ago, but there are many things happening here, and we wanted to share some new things with you. So the webcast topics, it's mostly a live demo presentation. And what I'll try to do in the time span of about 30 to 40 minutes, I'll try to design a simple part. So instead of watching videos and things like that, you will have a good idea of how fast, how quick you can be with this Workbench. We'll start with just a little short overview of CATIA Composites portfolio, as well as design methods, and then we'll cover just one of the methods, because actually there are several suitable for different types of parts and different designs. And we're going to be covering zone-based design method, which is the most generic, the most general way. There are some other more efficient ways for monolithic parts and when you re-engineer metallic parts, etc. But the zone-based design is the most commonly used. So we're going to cover material properties, preliminary design, detail engineering design such as splice generation, etc., manufacturing preparation such as draping simulation, flat patterns, and plybook. We'll talk a little bit about integration with FEA analysis, which is done very well in CATIA, and we'll finish with a summary and some Q&A. So just a couple of things regarding CATIA Composite solutions. So the motto Dassault, which is we partner with for composites, is the discipline is switching from being a black art to industrial discipline, and that's exactly what's happening. So just a few years ago, it was mostly a black art, which was the knowledge needed to build composite parts was embedded in people's heads, expertise needed in-house, etc., and things are rapidly changing. What CATIA is offering right now is the complete end-to-end solution. So it starts with preliminary design, where you can create zones and do some basic engineering definition. You can create IML and 3D mock-up, as well as create ply stack-up, engineering drawings, and things like that. So at this stage, you can exchange data and run FEA analysis, which means before you embark into manufacturing detailed design, such as draping, darts, material access, etc., you can actually verify your design, and if needed, add reinforcement plies, change number of plies, orientation, so on and so forth. And CATIA is very well integrated with FEA analysis, of course, with the native analysis such as Simula and Abacus, but just as well with Patron, Nastran, FEMAP, and ANSYS as well. So once the engineering design is complete, you move on to the manufacturing detailed design, and you prepare your part for manufacturing, which is you can simulate draping, which is how the fabric, how the material drapes over the OML surface. If needed, you can design darts to remove wrinkling and other draping problems. You can add material excess for trimming after the production, account for spring back, do your ply flattening, plybook. So once this is done, at the very end of this workflow is manufacturing output or export, and there are dedicated solutions in which you can study nesting, cutting, laser projection, fiber placement, and programming the layup and all that goes. So we're not going to be covering all of that. It would take perhaps a week to go into every nook and cranny with this process, and that's not the goal. What you want to do today is to cover just one workflow, which is zone-based design. Now, as far as design method, there are several in CATIA, and the three dominant ones are presented on this slide. The first one is the zone method, which is originally or historically was the first one after what was called manual ply creation, and it's the most general design method. With this method, the part area is split onto zones. And a zone essentially is an area with constant thickness and the same laminate. And then the software creates actually plies automatically from zones. So this is what we're going to be covering today. Now, there are some other new developments happening as we speak, and actually quite a bit has been already done and ready for industrial implementation. So one of those methods is a grid method. It's actually a variation of the zone-based method. The main difference being that the zone's boundaries are defined by a grid, such as spars and ribs. So in this picture, you can see the model of a wing, aircraft wing, and it's just natural that the zones, so the laminate thicknesses, are those areas between spars and ribs, just like a grid. So with this approach, it's the extremely efficient and very, very convenient way for designing stiffened panels, such as presented on the slide. And another very interesting development that's been completed already and it's available for use is solid slicing method. With the solid slicing method, you start with a solid model, and then you slice it to actually create plies. So of course, this is the most efficient method for designing monolithic parts, but also it's very convenient and useful when you want to re-engineer metallic parts, legacy data. So you can take your model you designed in before, maybe some other, or even SolidWorks, and actually use the solid model to create plies. And as it says here, it can also be used for working with imported solid models such as SolidWorks, Solid Edge, and other CAD systems, including ProEngineer and so on. But as I said, I can go on about those methods for a week. That's not the goal. We're going to cover just the zone-based design. And I'm going to start a software demonstration. And as I said before, all I'll try to do is design a simple part, given the time constraints, of course. But I want to show you all the steps involved. And of course, you need to prepare your model prior to embarking onto the composites design, into composite design workbench. And the preparation consists of, first of all, you need to have your OML surface. That's the green one presented here. How you design this surface? Well, you can use CATIA, or you can use imported geometry, whichever works. But it has to be OML or tooling surface on which we're going to be placing plies. And secondly, we need to somehow determine the ply boundaries. And typically, it's done by creating a network of curves. So you see there is a bunch of curves placed on the surface, which define the boundaries between different laminates, different thicknesses. Again, how you create it, you can use CATIA if that's your main CAD system, or just as well, you can use any other, just import it into CATIA. So once you have your model prepped, the next step, you got to start with materials. And as far as materials, I have a material library open here. It's a composite catalog. And these are composite materials in my kind of sample library. So typically, this data is available from material vendors. For instance, if I double-click on this one, which is carbon 0.27, we can see that actually it has a composites tab in here. And it turns out we can work with different kinds of materials. It could be unidirectional, bidirectional, such as a fabric. Just as well, it could be non-crimped fabric or non-structural. Undefined, this is something like a chopped mat when you deal with injection molded materials and so on and so forth. And you put in the properties, such as thickness, maximum deformation, limit deformation is accounted for when you run producibility analysis and you want to determine the shearing deformation in your material when you lay it over the OML surface. Other things such as fabric width, weight per surface unit, and even cost. We can actually estimate the cost. And if you want to integrate or run FEA analysis, there is another field which says analysis. You see this one is orthotropic material 2D. So we have orthotropic properties such as longitudinal, Young's modulus, transverse, Poisson ratio, and all that goes. Okay. If you check some other, let's say I'm going to double click on this fella and I'm going to composites. So this turns out is a unidirectional, which means essentially it's a toe or fibers placed at angle. That's not a fabric. And again, a whole bunch of properties. So once you have a material catalog done, and as I said, most of the information is available from the material vendor, the next step is to actually put those materials into the model. And we start with creating what is called composite parameters. And we need to add material. So hit add material, browse to a catalog. Let me find it. That's in my personal folder. I think it was marketing. Yeah, that's Webcast CPD, and I'm going to be using this one. So it shows me all the materials available in that catalog. I can browse through families if I have several, and I can select as many as I want. Do I have to absolutely use every single material in my model? I don't. If I knew exactly, starting this analysis, which materials I would want to use, I could pick only those, but it never hurts to pick as many as you want. All right, so it puts all the materials in the model, and it shows you, by the way, all the properties. So you can get a quick reference of the type of material. By the way, honeycomb, you see it's undefined material, again, cure thickness, uncure thickness, fabric width, and all other parameters. And it actually puts those materials right in the specification tree. As you see, it's all associative. The second step, we need to specify directions. So the default setup is 0, 45, negative 45, and 90. And we can add as many directions as you want. So when you click on a direction, it shows you the color, and we can change it if needed. For instance, for the 0 degree, I'm not a big fan of the gray color. I kind of prefer the brighter one. So let's say I'm going to use the yellow, bright yellow one. So 45, that's red, okay. So everything is color-coded. Whenever I'll start creating plies, the color of the ply will tell me what's the orientation of the fibers in this ply. Negative 45, bright green, good enough, and 90 is blue, good enough. And just for fun, I'm going to add another direction. Let's say I want to have 60, just in case. So there's going to be 60 and 60. And I'll use a unique color. Which one? Brownish. Okay. And I can also specify laminates. So if I click Add Laminate, there are two ways. I can specify a laminate using stacking sequence. So pretty much I specify the sequence of the plies right away. So I can select the material. Let's say the bottom ply should be carbon, orientation. You see it gives me the options that I have, and hit Add. So let's say the next ply I want to have the same carbon, but now at 45 degrees. Hit Add. And so I go. So this lets me specify the stacking sequence right away. The second method is using thickness flow. With the thickness flow, we don't really sequence the plies yet. We only tell the system how many plies at which directions we want to use. So for instance, let's say this thickness flow is using carbon 0.27, and I want to have, let's say, about 4 plies at 0, a couple plies at negative 45, positive 45, couple plies at negative 45, and maybe, let's say, about 4 plies at 90. Okay. When I hit OK, it actually puts the laminate in here. I can specify as many as I want. Again, do I absolutely have to use them all? Not at all. And another very convenient way of using or putting laminate into your model, just using import. So for import, you need to create an Excel spreadsheet. I'm going to show one right here. It says laminate to import. Okay, so basically you see that's the name for the laminate, type, thickness flow, or stacking sequence, so orientations and materials. So let me try to import that one just to speed things up. So I'm going to remove this laminate, and instead I'm going to go import, and I'll pick the one that I had and hit import. Okay, so it says import successful, all good. Now let's review laminate 1. If I hit edit, turns out, yeah, it has 4 plies, 0 degree, 1, 1, 1, and so on. So I can review the laminates. It showed me the thickness, the low, etc., and I'm done. So at this stage, I'm done with creating composite parameters. And from here, I could do what is called the manual plies creation. So I'll give you a quick example. That's the way of how it was done 10 years ago. It's still available in CATIA, but I want to explain what's the problem with this approach. With manual ply creation, let me create just a couple plies. So I'm starting with the ply group name, surface, that's my OML, draping direction. As you can see this red arrow, this is how the stack will grow from the OML. Am I okay with this one? Fine enough. And rosette defines the orientation of the ply. The X direction is 0 direction in the ply. Okay, and I can start creating the plies. So let's say I want to start by creating, you see it creates stacking engineering here. I want to put a ply as a ply group, and I want to create a bunch of short plies at the leading edge of this sort of surface. Okay, that's my first ply. Attributes. Which material I want to use? Well, I want to use, let's say, this fella. Direction, 0 degree, and hit OK. So what I ended up with, I actually created the first ply. So at this point, I can use copy and paste, and let me copy and paste it several times. I'll just copy and paste it a few times. Okay. So it seems to be pretty quick, and actually, by the way, at this stage I can change material. For instance, you see ply 1 shows 0 degree. Orientation, let's say my second ply I want to have at 90 degree, just double click ply 1. Okay, and go to attributes, and instead of 0, well, I'll just change it. Okay, I'll create a couple more plies. I want to cover, let's say, those short plies with a bunch of larger plies. And I'm going to create another new one. It's going to be the same plies group. And I'm going to create a contour. So let's say my next ply will be, actually, I'm going to remove this one. Got to make sure I'm selecting the curves instead of selecting the plies. So it's going to go up to here and up to here. Okay, and attributes. Fair enough. I'll just use copy and paste a few more times because I want to show you what's the result of what I'm doing. Okay, so I'm going to do copy and paste a few times. Okay, so I have a whole bunch of plies. Now here's the problem. If I do what is called a ply exploder, so that's plies group. Let's say I'm going to do magnified, and if I hide the OML, okay, here's what I ended up with. So what I was getting to, you can work with manual plies creation. This works just fine. It's available with CATIA or FiberSim, any other package. The problem is working with ramps. So here I should have a drop-off. Instead of kind of steep drop-off, I would want to have like a gradual ramping down from thicker zone to a thinner zone, but it's not there. Could I do it using manual plies? Yes, certainly. What's the problem? I would need to create a lot more of those curves. So basically, for every ply, shorter plies, I would need to create a curve on the surface. Very tedious work, but there is a better way. So now we're going to be using zones. So I'm going to get rid of this one, manual plies, and I'm going to start with zones. So I will have 3 zones in this model. The thicker one is the shorter plies at the leading edge. Then there is another zone, and then there is another zone, even thinner. So now instead of creating a group of plies, I'm going to create a group of zones. So zone group name, fair enough. Surface, that's my OML surface. Draping direction, okay, I'm good with that. Rosette, select rosette. And these are display options. I want to just see the thickness of the zone and just hit OK. So my first zone is going to be the thicker one. So that's going to be from here to here. What's a laminate? So right now I have 3 laminates in the model. The thickest one is laminate 1. Just put it in. Rosette, it automatically takes it from the group and just hit OK. So what I ended up with, as you see, created a zone. I created a new entity in the specification tree. It says zones group, and that's zone 1. So let me create a couple more zones. So the next or thinner zone is going to go from here to here. Okay. And instead of laminate 1, I'm going to be using thinner laminate. That's this fella. So you can tell that, okay, the thickest was 2.47 millimeter, and the next one is 1.64. And the last zone, the thinnest one, that would be from here, and laminate, that's the thinner one. Okay, so can I see the result? So actually at this point I can generate a solid from zones. There is no detailed plies as yet, and still I can create a mock-up, an approximate IML, which you can pass on to other people in my design group, so they could design brackets or fasteners to be attached to this panel and so on. So I'm going to try to create a solid, okay, and I'm going to generate a solid, and there you go. You see, it's a solid model. The problem is, as you see, the solid doesn't have ramps. It has abrupt transition from the one zone to another. To create ramps, I'm going to use now what is called transition zones. All right, so I'm going to get rid of that fella. And I want to create transitions. So again, I have some geometry pre-created for transitions. So that was transition zone contours. And let's say I want to transition from the thickest zone to the next one up to here. So I'm going to create transition zone. The underlined zone is this fella. And just select create a contour. Same as before. I'm just going around the zone. Oh, wrong one. That would be that one. Okay. Let me recreate it. Got to be careful with the selections. So zone, this one, and I'm going to go from here to here, then on to here, and then on to here. Okay, now it's green check mark. All is good. So here's my first transition zone. And I'm going to create another one. I want to ramp from the middle zone to the yellow one over this area, this width. So the underlying zone is zone 3. And the contour is going to go from here to here. Green check mark. All is good. So now if I try to create a solid, which I did before, that's a drop-off. That's associative solid from zones. Okay, now you see it shows nice ramps right there. Okay. And I can also generate, instead of a solid, a top surface, which I'm about to do, because eventually what I will want to do is to actually put a core on the top of this bottom stack, on the top surface. So actually I'll really quickly create the surface. Okay, now it's going to be top surface. Okay, so same thing, but it's not a solid, it's just a surface. I'll hide it for now, and we're going to move on to generating plies. Okay, so let's see what we can do from here. Well, to automatically generate plies from the zone, there is a tool that says plies from zones. Okay, let me try that. So which zones group? That's zones group number 1, all good for me. Let me try it without using a stack-up file. Create plies in new group, zones with taper. These are transition zones, all is good. And I can run it. And let me visualize the plies. Okay. I'm going to hide the OML, and CATIA did create a bunch of plies, but I'm not very happy with the sequencing. Okay, so basically it uses some default rules, internal rules, to create those plies, etc. But it's rarely, very rarely, that you are happy with this default sequencing. So instead, what you're going to have to do is to actually create the stack-up file prior to creating plies, and in that stack-up file we're going to resequence the plies. So what I don't like is with this one, I have, as you see, 2 plies with 0-degree orientation at the very top. Not a very good idea. So I'll get rid of the stacking for now, and now before I move on to generating the plies, I'm going to unhide the zones. I will create a stack-up file from zones. Okay, so zones group. Just pick a name. You see it's an Excel spreadsheet. So there's going to be new stack up. hit OK, hit OK. Okay, so it actually creates a file with a default sequencing, and I can change it. So, for instance, in this specific case, well, I don't want to see two plies at the very top with 0-degree orientation, so I want to insert maybe 90 degrees in between. Just use your tools, Excel tools. So we can resequence and reorder them anyhow we wish. We can also do renaming. For instance, I don't like this sequence 1, sequence 2. I'll use something shorter. So pretty much at this point, what I'm doing, I'm sequencing the plies. And that's what will be used when I actually create plies. So once done, save it. Well, I won't be saving. I'll be using a pre-stage file. But let's see how it works. Okay. So I'm going to repeat the same process. By the way, I don't need this fella either. So let's see what I have. There's a group OML. Okay. And I'm going to create plies from zones, but now I'm going to say use stack up file. And I'll pick the one that I have here, well, edited before. Plies in new group, zones with taper. And off you go. Okay, so it also created plies group and a whole bunch of plies, but now when I check the sequencing, which is using the ply exploder, okay, I can now see that you see the plies have been reordered indeed. Like in this specific case, I wanted to avoid to have two plies with the same orientation at the top, and I've just done that. Okay, so that's the first way, and this is using transition zones. And one might ask or have a question, okay, what do I want to have a custom drop-off? Because with the transition zone, the drop-off is even. Let me show what I mean. I'm going to hide this and hide that. So as you see, the ply drop-offs are uniformly spaced from one boundary to another. So if I wanted to create plies non-uniformly spaced, create like some kind of a custom transition with different offsets, etc., I would have to use a different method. We're not covering it today, but the method would be to use full plies and ETBS. ETBS stands for edge to be staggered. And with this approach, it will also create a file in which I can actually customize the offset from one to another. Okay, but let's say I'm happy with what I have, which is the plies, the current one. What are my next steps? Well, by the way, at this stage, I can also create plies or solid from plies. So before, if you recall, I had a top surface from the zones, but now I can do it with the plies. Okay, so let me hide. I'm going to do some cleanup here. I want to remove exploded surface, which was that one. I'm going to unhide this back and top surface from zones that are needed at this stage, and group OML. Okay, so I'm going to create now solid from plies. You see there is another option. Now I have plies, because before, if you recall, I only had zones, which is conceptual design without the plies. Now let me see if it works with the plies, and I want to have exact solid, complete second. Works enough. Okay, so now you see the solid I got as a result shows me those steps from one ply to another. So that's another level of kind of accuracy, and if I had uneven staggering on uneven offsets in the ramp or drop-off zone, I could easily see that in my solid model. Okay, I'm going to hide it for now. All right, so at this point I can also use different kinds of design review tools. So we've seen this ply exploder tool, extremely convenient thing. There are some other options available. For instance, I can do a cross-section. So if I do a cross-section, what I want to make a cross-section, I want to go through the plies group. Curves or planes, you can create a plane. Let's say I want to go through the middle. Okay, so if I zoom in, you can see it created a nice looking cross section, so I can see transitions. And remember, every color means orientation. So looking at this one, I can tell the yellow was 0 degree, the red was 45, green negative 45, 0, 19, 0. So I can examine my part, examine my model quite carefully, and see what's going on here. Okay, what are the other tools? I'm going to get rid of this one. Coarse sampling. If I want to determine the ply sequence at certain location, that's called coarse sampling. So I can select, let's say, this point, hit apply. So it tells me exactly what are the plies and orientation I have at this location. And I can analyze at any point. I can pick any point on the surface or select a pre-created point. And another convenient tool is numerical analysis. So let's say I want to do maybe some mass analysis for the stacking I have. Just click the apply groups. Material, all materials, and it gives me properties such as area, volume, mass, COG, which can be exported. If I just want to get properties, by the way, cost included, just for specific materials, let's say I want to know how much Kevlar I'm going to use in this model, I would select that, and basically you see it tells me the area and so on. So I can go with materials and go back to all. Okay, I'll cancel it. Now, another little thing I wanted to show you is core. Let's say what I want to do is on top of this bottom stack of plies, I want to put a core. So I'm going to hide and show a few things here. If you recall, I created top surface from zones, which becomes now the reference surface for the core. Okay, and I'm going to hide this one. And I have it pre-staged. So basically, I want to create a core with the outline roughly like this, purple curve, purple contour. So now I need to create with a group of ply for the course. That's going to be, you see, I'm picking the new reference surface, which is the yellow one. Draping direction, good enough. Rosette, I'm going to use the same rosette. Okay. Now, instead of using a manual ply, I'll actually create a core. Okay, so it says where you want to put the core. It's going to go into plies group number 2. Geometry, there is a nice tool which lets me create the solid geometry automatically, and I'll do, let's say I'm going to use this base contour. Oh, actually, I failed to do one thing. Hold on a second. So this contour actually is created on the green surface. I need to project it onto the yellow one. It's done pretty easily in CATIA. I'm going to switch to generative shape design. And I'll just do a simple projection, normal, and I'm going to project this purple line onto the supporting surface, and there you go. Okay, so now I can hide this, and that's the contour of the white one that I'll have to use. So going back to Composites Design, create this. It's going to go into the plies group number 2, geometry. Okay, selection, I'm going to select this one. Parameters, let me try those defaults. Okay, and there you go. So material, well, apparently carbon is not a very good idea. I'm going to use a honeycomb material. Direction doesn't really matter. It's not being flattened. And here's the core. So if I needed to cover it with the core with another bunch of plies, I would also need to create another surface on top of it, and then use the same approach with the manual plies and so on. But that's not the point. Again, given the time constraints, I want to move on to other things. If you have any questions regarding that, I can answer those at the end of the webcast. All right, so we're done with engineering stage. Now we want to see how whether the part is manufacturable. We want to get flat pattern and things like that. So I'm going to do some hide and show here. I have stacking, which is good. I'm going to hide these. I don't need solid core geometry. I'm just decluttering the view for now, top surface from. Okay. And what I want to do is run what is called producibility analysis. With the producibility analysis, I can actually analyze how the plies are going to drape over the OML surface. So that's this tool, producibility analysis, and tells me, okay, which ply you want to try. Let me try the last ply, P9. Let's see, by the way, it is at 0 degree carbon 0.27. Okay, and the starting point, imagine that you drape your ply over the OML surface. That's where the ply or fabric will first touch the OML surface. Let's say I want to start with the middle. So it shows me, by the way, warp and weft direction. There are many options for propagation type. So actually, that's one of the strong points in CATIA, because there are some very unique algorithms suitable for specific types of materials, such as stretchable, non-stretchable, and so on and so forth. This is a very basic material, so I'm going to use just distortion 5.5, and I can run producibility analysis. So it shows me the mesh, and the mesh is color-coded, and the information it's telling me depends on what I requested here. So first of all, I can analyze the results by deformation. And the deformation is the shearing angle. Essentially, when I drape my fabric over the mold, the formerly rectangular cell will become like a skewed a little, so it tells me by how much. And the color, the blue color, means it's under the, as you see, the warning angle 5 degrees. And you know, this one, it's pretty simple model, so it's pretty good. And the second one, I can also check deviation. So deviation tells me by how much orientation of my fibers deviate from theoretical orientation. So if I want to have my fibers aligned along a certain direction, let's say across this part, to achieve best, you know, weight to strength ratio, beneficial for bending, etc., etc., I want to make sure my plies or my fibers are aligned in a certain way. So this deviation thing tells me by how much the actual orientation of the fibers deviates from what I want it to be in my design. I can also check for material width, so material width is good enough, and I'll just hit OK. So let me analyze the second ply. I believe I had some unidirectional ply in here, okay, and that was Kevlar. Yeah, there you go. All right, so I'm going to do another producibility for this fella. That's, by the way, unidirectional. Okay, and I got to select a point, start from the same. You see, it shows me only the fiber direction, and that's another producibility analysis. As you see now, it doesn't show me the grid because the material was unidirectional. It's not bidirectional. It wasn't the fabric. So, so far so good. I'm good with that. There is no need to do any darts, which would be perhaps the topic for some other webcast later on. But once I've done producibility, I can actually produce a flat pattern. Okay, so I'm going to do a flat pattern real quick. I see there's a flattening. Which ply I want to flatten? Well, I'm going to flatten which one? P9. Okay, and actually I had a plane created here. This is where I want to place my pattern. Yeah, flatten. I'm going to unhide it. So because I don't want my flat pattern to appear or overlay over the main model, I want to put it on this plane. Okay, and I want to locate it at that point. So material roll, good enough. Hit apply. And here's your flat pattern. Okay. Now the way it works is it actually computes intersections between the curves and that grid that you've seen. So that's why you end up with those, you know, a bunch of those points, etc., which can be optimized. So there's another nice tool that lets me optimize the flat pattern. So I'm going to select that. Is it good? Okay, let me try with the default. Yeah, it's a much nicer contour. So basically, it was able to smooth all those little segments, tessellation, etc., and get a nice looking flat pattern contour. So this way I can get flat patterns to all my plies. And as I said, there are several flattening algorithms which are suitable for different kinds of materials. So once I have that, I can export my plies. So export ply, what I want to export? Well, I just want to export, let's say, this one. You see I can export it to IGS, to DXF. So many different options. When I hit OK, export to DXF, then it can be imported into your laser cutting machine and actually produce the ply on the floor. Okay. And also, I'll show you the ply book. If you want to create a manufacturing instruction, kind of running out of time quickly, but anyway, I think we still have a few minutes to show you that. So I want to produce a ply book, okay, and I'm going to start by creating a drawing, drafting. Okay, and I'm going to change the scale quickly. So that's the sheet scale, and I need to do some prepping, which is I want to show the plies, which is I need to get exploded surfaces. So I'm going to do exploded. I'm going to do plies group number 1, and I'm going to do it real scale without any magnification. Hit apply. Okay. So now I'm going to start creating views, and I'll just do isometric view for simplicity. So I'm going to do isometric view. Default generative style, switching back to the model I had, and what I want to show my OML, so I'm going to select OML. So which orientation? Let's say I want my isometric view to be roughly like that. Okay, and that's my first view. That's just OML. So I want to overlay the ply over it. So I'm going to create another isometric view. Now instead of default, I'm going to use exploded only. Switch to the model that I had, and just select the first ply. And select this. Okay. So now I have two views, and I want to show this in a raster mode. I'll do it again very quickly. Instead of exact view, I'll use raster. So yeah, as you see, it's all done live in real time, what I'm doing right now. Okay. So, and I'm going to superpose it with the other view. Okay. So that's my first view. And now I can actually create a ply book, which is automated. So 1 sheet per ply cut piece works for me. Gonna go there. So that's plies group. Hit OK. And it starts, as you see, automatically creating sheets. What I requested was 1 ply per sheet. So if I go to the first one, that's my first ply. I can tell orientation. You see the second one, the third one. Okay. And that's your ply book. All right, and another little thing I'm going to spend maybe roughly 5 minutes is I did say that this workbench is very well integrated with analysis. So I want to show you a very simple model, but I want to give you an idea how it works. So I have this model fully designed. So you see it has a stacking, it has plies, materials, and all that goes. And I want to run a quick FEA analysis. All right, so I'm going to switch to the analysis and simulation, and that's generative structural analysis. So it starts a new workbench, static analysis, fine by me. It shows me ply, same model. And I'm going to create, adjust the mesh. So right now, what is about 14 millimeters? I'll use about 4 mil perhaps mesh. Okay, if I want to check the mesh visualization. Is it good enough? I think it's good enough. It's a parabolic element, second degree elements should work fine. So at this point, by the way, I can hide the plies. I don't need to see them. And the next step is actually the core of the whole thing, which is, as you know, in composites, it's very difficult to compute those matrices, which are material properties for the stack of laminates. But there is a nice option which automatically do it for you. It says imported composite property. So I'm going to hit that. It says support. That's the surface. Analysis, I'm going to be analyzing by ply. And ply selection, I'm going to go back and select the plies group. Transfer producibility will actually transfer the actual orientation of the fibers, and hit OK. Yeah, that should be good to go. So let me maybe try to apply some simple boundary conditions. I'm going to fix, let's say, this edge end of the part. So that's going to be 1, 2. Pretty much fixing this edge good enough. And I'll apply a pressure to the top of this part. And I'm good to go. Material type is not supported. Well, I didn't want to do that. You know what, we're running out of time. I'm sorry, I'm going to have to skip that. I guess somewhere along the line I put the wrong material in this model. It could be one of those honeycomb or something like that. But basically at this point, it should run and I just get results by ply, which is failure criteria such as side wood, side heel, and so on. Maybe during the Q&A session, I'll try to figure out what exactly went wrong here, and we'll show you results as well. So, Karine, how are we doing as far as the time? Do we have a time? Do we have a time for a video, short video, highlighting maybe a few other things in this solution, this workbench?
Sure, we can certainly give it a try and see how it will play.
Okay, it's about 5 minutes. So as I said, it doesn't really cover, I mean, gentlemen, ladies and gentlemen, it doesn't really cover the breadth of the solution at all. What I've tried to do is show you real time the example of a design, but there is a lot more, and I just wanted to show you a quick video. It's some kind of like a teaser video from the saw, because there is a lot more available. So I'll be stopping it from time to time, commenting on what exactly was going on, and I'm going to start this video. It takes 5 minutes, so it's not like a huge sales pitch, just something quick. Okay. So here's the motor to industrial discipline. Nice looking pictures. I hope it's not, there isn't much of a delay.
There's a little bit of a delay. There's no sound, but if you're going to speak over it, that's fine.
Yeah, I'll be just commenting. So one of the things that is addressed is legacy IP reuse. And what I wanted to comment is for many companies, well, aerospace in particular, you might want to reuse your existing designs, and which were metallic parts. How do you do it? Well, fortunately, CATIA has this method which is solid slicing, which is exactly designed to handle those kind of things. Okay, so I'll proceed with a bit more. Okay, so that's a metallic part, and you can put it in. Okay, and then once you have it in, you can actually re-engineer it into a composite part using this solid slicing method. Okay. Now, also, what is good is the design in context of assembly. So in CATIA, you can design your parts in the context of assembly, which means this way you can ensure the proper fit between the parts, connections between the parts, fasteners, etc. So this little snippet in the video shows you an example of a grid-based design. So with the grid-based design, you see the zones are designed as a grid, and there are some nice looking tools which can let you actually specify the sequences, the stacking for each cell in the grid, and so on. Okay, so that's grid method. And once you have the grid, same as with the zones, with the simple zones, you can create plies. And also you can create, as you see, the solid. So this solid, as you can tell, is a lot more complex than I had in my demo, because it's a lot more complex model shown in this video. Okay, so that's IML or solid mockup. Now, what is also good, if you stick with CATIA, you can create what is called templates. That's little snippet. The next one shows you that how a template part can be instantiated in CATIA. Okay, that's PKT, product knowledge template. Okay, so you can account for manufacturing constraints such as splicing the plies. You can get documentation in 3D. This is something that I didn't show, but you can create three-dimensional FTNA tolerances and annotations, and just as well as I did in my demo, you can create the ply book. Okay, in V6, another important aspect is concurrent engineering. If you use composites with V6, which is CATIA and Innovia together, you use 3D as a common kind of language, communication language between different groups, and you can actually let several members of your team access the same data in the data management, in the database, and work from there. Integration with FEA. This is something that I mentioned, unfortunately didn't work as intended. And as you see, you can get the results quite quickly between FEA and so another aspect is archiving, which is also addressed with this solution. You can step or save your models as step files and other models as well. Let's see what it shows here. Next. Yeah, very quick design analysis iteration. Some other, by the way, solutions available. If you work with Simulia, Abacus, there are some very unique simulations. That's an example of a crash simulation. We have something like a bird hitting a propeller or something like that, and you can actually get simulate the penetration or destruction of the part. Okay. Flat patterns degeneration, okay, that's the same predictability thing. And actually, as I mentioned, CATIA has some unique solutions in here. And you can also get simulation of virtual shop floor, such as you see laser projection, manufacturing process, work instructions, all kinds of plies. So it's a pretty powerful lifelike experience. Okay, yeah, of course, it's not just aerospace. Composites are making their headways into other industries, which are roughly shown on this slide, in this video. Okay, so that's a bit of a teaser video, and now I wanted to go back to the summary and get to the conclusion of our presentation today. Okay, so just as a summary, as I mentioned before, CATIA offers, this is our firm belief, the most complete, integrated, and scalable solution for composite, including but not limited to. So first of all, you have end-to-end model associativity from conceptual design to manufacturing output. Very easy to make changes. If you work with any history-based, feature-based CAD modeler, you know exactly what I mean. Now, it has a very rich set of different design methods, which is suitable for different types of parts to be designed. You have your manual plies creation if you want to. You have a basic zones approach. You have grids approach. You have solid slicing, and there are some other methods as well, such for different types of ramps, tapers, etc. Another strong feature of this solution is a very tight integration with FEA, including crash simulation, crack propagation, delamination, and others. And another firm belief, another differentiator is that it has best-in-class draping simulation and flattening algorithms. Yeah, and I think we are perfectly on time. We have, I believe, a few minutes finished. So, Karen, did you want to add anything about us as a company before we get into Q&A?
Well, I just wanted to have this slide up here. Thank you very much, Iouri. That was great. And you did it all within an hour? Or just under?
I tried.
Yes,
I tried hard.
So just to let everyone know, we do offer here at RAND 3D training solutions, of course, software solutions, and consulting services. And I should have mentioned at the beginning what an expert Iouri was. I don't need to tell you now because you've heard him speak, but Iouri works for RAND 3D. He's been with us for many years. He has his PhD. He's an engineer. He's an expert in many things, including composites. So we're really thrilled that you were able to help us today deliver this webcast. And if you'd like to see Iouri in person, we've got a couple of opportunities coming up. We are attending an event next month. Is next month June? Yes, next month. So June 21st to 24th, we're going to the NAFEM show, which is Simulia-based. And Iouri is our expert there as well, so he will be at that show. We have an exhibit there. We'll be in the exhibit hall. So if you happen to be in the, I believe it's in the San Diego area, then do come to the show and come seek us out and find Iouri. And we've just confirmed today that we will be running a composites class in July 20th in Charlotte. So if you are in that area or can travel to that area and would like to take a class with Iouri, then please contact us. We have all the information about that class and all of our other classes and software and that on our website at rand3d.com.